So then let's do the final session on SPM programming, because next session will be a Q&A on the program project report. And yeah, let's maybe first rehearse what we went up to and where we are. So we worked on this function which which includes pre-processing, for which we wrote a function that is called cbfmi preprocess, and it's a subfunction of the script. And yeah, this we discussed and did everything. And then last time we started also do the statistical modeling. And as I also said at that point, the crucial thing about formulating GLMs and estimating them in SPM is to bring together the data, so the image time series that results from pre-processing, and the experiment in terms of the onsets of conditions during an FMRI run, which make up together the design matrix, because it determines how many rows the design matrix has in terms of the number of data points / the number of EPI volumes, and how many columns the design matrix has in terms of the number of conditions that are being modeled, and of course the specific content of the design matrix, basically in first level analysis, having hemodynamic response functions whenever there was a stimulus, in the most common way to analyze fMRI data. So we went a little bit into participant level GLM modeling, and maybe let's go where we left off. So maybe I should close this one. And this one I will talk about in a second. So we essentially just set up again a data directory for the GLM modeling, and then we discussed this bit here in terms of the timing parameters, which need to be specified so that the design matrix can be constructed by SPM, and how this works in detail. This is in my book, and I also have my own code to do that, but that's a completely different question, because we are here more on the higher level analysis. And that's what our interest is. And then we basically went up to here, where we specify the files that we want to analyze, which are the smooth, normalized, and realigned files of a given run for a given participant. So this is the participant, and this is the run. And then we essentially ended on the fact that we have to somehow get the onsets of the different conditions during an fMRI run. And these data were by the PhD student at that time, which was me, saved. Please be known here. Saved in these kind of files. So there was a MATLAB script that ran the experiment. The MATLAB script recorded also when a certain stimulus was presented, and there is documentation of this in the folder that you all have for doing your project report. The crucial thing was that in this files, there's a warning, because this is related to some old input-output trigger reading stuff. That's really not important. So there's one crucial variable in there, which is called event log, which is fairly standard also if you think in terms of bits format. So this is basically a long array that contains the time points of all events that happened during a run with respect to the run onset. So this is time here, and the run starts and the experiment starts at time 0, and then in seconds things happen during the run, and at one point there's the last event that happens in this run. And of course one needs to know what these conditions are, and for our purposes here the main interests are these cont2 and cont1. So cont1 was the presentation of a high contrast checkerboard, and cont2 was the presentation of a low contrast checkerboard in the left visual field. Of course this one needs to know, and the bits format for event logs or for events is essentially the same as this. It's just a little bit more standardized. For example, that, I don't know actually what is, whether the onset times are in the first column and then the explanation is in the second column, or the other way around, I don't know right now. But the format of bits for fMRI events is really, really close to that. There are possible other columns with more explanations, but essentially this is the format, the bits format, and this also shows that because before bits was around, we already knew how to save these things, but of course with bits the nice thing is that it's now very standardized. So this I think should be clear, and of course it only gets really, really clear if one knows the explanations for these things. So for example, target on, there was this there was a fixation cross that somehow sometimes went to an X, and people had to do a fixation cross task. So then was the target on, and then people were detecting it, so they pressed the button, and then was target off, and so on. So this depends a little bit on the particularities of the experiment, but the format, saving the times and when the meaning of events together, that's also bits format. Yeah, so that's relatively straightforward. The thing now is that SPM, if you think about the design matrix, it wants before the convolution with the HF, it wants the onset times for a given condition in the columns of the design matrix, and then one has to decide which events and which conditions one wants to encode in the first level fMRI analysis. Of course, we're talking only about first level fMRI analysis right now. And then one needs to present SPM essentially the conditions and onset times for a given condition. So this is how SPM works. We can look at that from the SPM GUI if we want to make that clear. So what we want to do is formulate a design matrix for each voxel, and of course, as you all know, for a design matrix, we need to specify what our regressors or conditions or effects of interest, however you want to call it, are. And I'll press this for a long time. Let's see what's behind this. Oh, it just comes up with that. So if we want to specify the fMRI model, which is a design matrix, we have to specify the things that we have already specified, and then we need to specify for each participant and each run essentially the data, which is the scans, and then the conditions. And for each condition, meaning a column of the design matrix, we have to specify a name, an onset time, and a duration time. And there are different ways for duration. So the typical thing for event-related designs is that one takes the duration 0, then one just has a stick function, which we have to convert with the HF. Of course, one can also take longer durations if one, for example, a block design. Yeah, so this needs to be specified. So for this, we need the onset times for a given condition. So that means we have to decide what our conditions are, and we have to specify and get from the data that we have in our event log. Oh no, I cleared everything. We have to get the onset times. So essentially we have to, from this, create a vector that has the onset times of condition 1 and condition 2 if these are the conditions that we want to include in our GLM design. And this is what we want to do. So, so this is then a little programming exercise, which I then, because I know that the master students would get crazy if I wouldn't do that. Because that would be like, I would get like 10 emails about this. I decided to just write this function because it takes like 10 minutes or less to actually convert the original data, how it was saved, into such an onset vector file. So this is what I now include here. So let's put this in here, pre-processing. It's called fMRI data pre-processing. And then we do some behavioral data pre-processing. Of course, one can do many behavioral data analysis, but here I just include conversion of event log data to condition onset vector data. And this is really the only thing I think one has to do by oneself in an fMRI data analysis. So one has to think how the experiment is presented. Then ideally these days one would save the behavioral data in the bits behavioral data format, which is essentially the event log data format that I just showed you. And then I guess maybe that it's already there, but soonish somebody will have written a function that converts bits event log data into SPM condition onsets and writes like a toolbox for that or whatever. So I think in soonish this also one does not do that with one's own code anymore. Maybe it's already there, I haven't checked. But yeah, for most of the time this was the only thing one actually needed to do in terms of programming for an fMRI data analysis. Now I have done that. And so I wrote this new function cbfMRI behavior. Of course, it's the whole thing, how we saved the data. It wasn't that nice because we had these specifications of the participants, so these codes. And for the behavioral data, I had this 3-letter thing because I thought 3 letters were cool, so that was also in the UK, where people usually have a middle name, and it makes sense to code people by their initials, and then they usually have a middle name anyway. So I wrote this little function, cbfMRI behavior, which turns the data as recorded by the experiment into onset files and save these onsets files in the EPI folders where we have the preprocessed data. So it's very simple what it does. It just loads the file for a given run and then goes over the 2 conditions of interest, condition 1, condition 2, and for each condition goes over the event log, checks whether there's an event called condition 1 or condition 2, and whenever there's an event called condition 1 or condition 2, it saves the respective onset, and then it puts the 2 onset vectors into an array that is called onsets and saves them. So this is something that would have created a lot of confusion hadn't I done it, but now I have done it, and things are nice and easy again. So we have the pre-processing. What we are concerned with is currently it's still a single run, which of course means that the master student should do this for multiple runs and for multiple subjects, maybe for overruns and over subjects as a hint. Sorry. Now for each run, there's this converted data, which then has a variable called onsets, and in onsets 1 there are the onsets for condition 1, and in onsets 2 there are the onsets for condition 2. So now we have the onset times. You see that there are quite some time between the onsets, so that was on purpose. So it's not a, if you want, fast event-related design, but there are we had like breaks up to 20 seconds between individual events because we wanted to do a single trial analysis in this case. Usually the events would be a little bit faster. Good. So based on this, we are now in the position to continue with our GLM script. And this is here. So last time we specified the timing parameters and discussed them, and then we went to data specification, which takes the smooth, normalized, realigned volumes from a given run. And now we can load this event onset function, which I'm doing here. So the data in the file which has the event onsets. And then essentially one needs to specify for each session the condition, and for each condition the name, the onset, the duration, some modulation, and some more modulation. And we don't do anything with modulation, so we just specify a duration of 0. And I included in the script 2 conditions, stimulus 1, stimulus 2, which correspond to this cont2, maybe I comment on that, cont1 and cont2 in original behavioral data file. Of course, this is not super nice that they have different names, but this is if one does. So this was also not the easiest data acquisition ever because we did simultaneous EEG-FMI, obviously, so we had to somehow, and this was also the first time that I did simultaneous EEG-FMI, so then not all things are perfect in this thing. But I could also call them here cont1 and cont2. I don't care, actually. Let's call them cont1 and cont2. But I think in one of these, but I think in the EEG they were actually called S1 and S2. Let's leave it like this. It doesn't really matter. I think it should be fairly clear that it's 1 and 2. And these are 2 conditions. So this then gets specified here, and then there are some additional parameters which are all commented on here. So which are all default values. So if one uses the GUI, then one doesn't have to do anything. So this multiple regressor specification is an alternative way to specify the conditions in the design matrix, or the counts of the design matrix, which we don't use. So this is not that important here. I think in multi-reg, what one can put in, which I'm not doing here, is to include the motion parameters, which one can do. So one can load the motion parameters and put them here. That's a nice exercise to put that in addition in there. And then, strangely enough, there is the high-pass filter cutoff specified. So you might know or might not know that the high-pass filtering in SPM is done at the level of the GLM modeling. So besides the conditions of interest, there are more columns in the design matrix which are never shown, which have a sign, a cosine basis set. So there are cosines of different frequency encoded, and they also get estimated so that essentially low frequency drifts are also accounted for as regressors of low interest. And the cutoff is 1/128, so that's why there's this one so the cutoff is at 0.0078 Hertz. One can change that, then one does a different high-pass filtering. That's how SPM does it. FSL filters the data, SPM models the filter. That's how they decided to do that. And then one can specify, or one has to specify more things. So one can, because this is a fairly general design matrix specification framework, this can also be used for other things like factorial designs. There's a lot of interest here. One can also model temporal derivatives of the hemodynamic response function, which is sometimes done to account for differences in hemodynamic response functions, and is based on the Taylor approximation, so a multivariate Taylor approximation that I'm not explaining right now. One can do that. One can put in interactions in factorial designs, which are of course not simply signaled as interactions, but as Volterra kernels, because it needed to be more complex than necessary. Global normalization of the whole thing is not done anymore. That was an old PET thing. Masking, this is some masking for, I think, voxels that don't have signal, which for which there's a cutoff. An additional mask could be used that only analyzes voxels in a specific region of interest. And then the covariance component parameters are modeled in what is called this AR1 model, which is not an autoregressive one model, but it corresponds to the covariance matrix that is similar to what an autoregressive one model would do. Again, details in terms of model formulation for the GLM that you can find in my book, which is not available yet. But you can also find this in the Friston 2002 paper B, what this means, at least in some to some degree. And then the whole thing just formulates the GLM. So let's do this. Let's end the thing here, and let's run it so that you see what this actually does. So this we also don't need to run right now. Just make sure that my thing is off. Which is due to the fact that at home and here I have different names for my Google directory. The difference being here. So this is now the FMI model specification using actually this sub-function SPM FMI design. So there are all the details of how the regressors actually created are in there. I've extracted that code also from my book to actually look into details how that's done. That's the trick is, or one thing that happens is that the convolution of the stick functions with the hemodynamic response function is done at a higher temporal resolution as the design matrix has. The design matrix temporal resolution is of course in terms of TR, because only for that there are values. But of course you get a nicer convolution if you do that on a higher temporal resolution. And once the convolution is done, then the resulting regressors are downsampled to the temporal resolution of the of the design matrix slash the data. So this has now run. What this creates is, I assume this what we did last time, specifies an SPM MAT file in the GLM folder. Of course, one can just look at this. And this is just a This is just a structure which has a lot of information on the design. So, for example, and one can actually, so if one goes into, for example, edit SPM fMRI design, I think one, no, that's, wait, how is it called? What's the, second, my great thing that always removes SPM. So what I'm trying to say is that if one wants to know more about what actually these fields are, the only documentation for this is in the SPM code. So here there's some information of what these things are. So data structure, design matrix structure, and then specific things, what things are. And the more one goes into details, the less clear it becomes what these things are, but there's some documentation. So not that it's completely unclear, but yeah, but you don't, there's not a like a textbook where you can actually read this and learn about this at the same time. So you only have the code and need to make some sense given what you know about the theory of the whole thing. So this creating this SPM mat structure, which for example has this design matrix thing, which for example in this field has the design matrix that we are interested in, but this might be high temporal resolution. Have a look. No, that's a low, the normal temporal resolution, so one can look at the SPM design matrix that we just created also directly, like this, for example. So that would be the design matrix with the first column being the onset and convolved with the hemodynamic response function of the first condition from 0 to how many volumes we had. Second condition, you see that it was either one condition or the other condition. It was kind of randomized, and constant offset, which is here in blue. I think it looks a little bit the typical way this is presented is like this. That is quite dark. Yeah, there are all sorts of normalization and so on steps that we don't discuss now. We can, of course, also inspect the design directly in SPM. Hello. So review allows to review SPM GLM designs. So same thing, we have nice visualized here, which data usually one cannot really read this, especially if one has multiple runs. There are here some other things. Covariance structure can actually also, it's not estimated and it doesn't tell you what the design is. Design orthogonality. There's also, where is that? Oh yeah, here it shows you how orthogonal things are. Oh. somewhere there was this. Oh yeah, this I mean. This shows the time domain regressors. So now I'm not looking at this from a design matrix perspective, but over time, although it looks a little bit squeezed in time. And what one can see is the power, the frequency power of the design, which is here at, I don't know, this. And one sees that with respect to the high-pass filter, so that one makes sure that one doesn't filter out the. So if one has a very low frequency design, which you sometimes have if you have multiple conditions, and then each condition only comes up every like minute or so, then of course if you filter out drifts like at the order of 1 minute, then you might filter out your signal of interest, and that's what one can see here. Yeah, this is how the HF is sampled in terms of the design. It's not that intuitive, and there's also no explanation for how this is actually computed and so on. So, yeah, something like the whole thing. Good, but this is creating the design. And so this is model formulation, and then of course the next step is model estimation. So estimating the beta parameters and covariance components. So any questions about model formulation at this point? No? Good. Then the next thing is model estimation. And if we look, you can look at this also at the GUI. So did I just close everything? No. So if we want to estimate a GLM something. Why is it? No, it's inline. Now we have two. So in terms of estimating a GLM, this is why I'm bringing this up. You essentially just specify which GLM and you want to estimate. Of course, the SPM map file holds the information about both the data and the GLM design. And then the only question you need to answer for yourself is whether you want to estimate this in a classical or a Bayesian way. The classical meaning a restricted maximum likelihood estimation procedure as described in the papers by Friston et al. 2002 and again described in Stark and Ostwald 2017. And there is some Bayesian estimation that nobody uses. So yeah, there are also 2 or so papers about how to do Bayesian estimation. I think it's yeah. I mean, you know, the whole issue about false positives and so on, that was just there last year. It was all in terms of classical statistics, and people wouldn't, if people would use this Bayesian, then there wouldn't be this debate. So nobody uses the Bayesian estimation. Whatever. So in terms of coding this is really simple because it just needs to specify the SPM MAT file, again information about the data and the design in there, specify that you want to estimate classical, and then it's being estimated. So let's run this and estimate. So what it's doing, of course, is that it has to estimate the GLM parameters for each voxel. So it extracts from the data files, extracts the data for each voxel, and then estimates the parameter based on this common design matrix, because it's a mass univariate analysis. The design matrices are the same for all the voxels. Estimate this for each voxel, and then of course gets beta parameters and covariance component parameters for each voxel as well. So the covariance component parameters are essentially the variance parameters, but there are multiple, I think like 3, because there are different covariance basis functions. Again, Stark in Austral 2017, which also shows that the whole thing doesn't quite work, the whole SPM premise. If you look into the supplement, that we do some simulations that actually show that parameter identification fails actually in 20% of the cases. But I think this was never really thoroughly investigated, so we also didn't want to make a big point about this. So I didn't want to write a paper that says, in 20% of the cases, SPM doesn't find the right parameters. I just put it in the supplement and left it there to rot. The way this is actually done is that what's happening here is that first it goes over each voxel, estimates the covariance component parameters and the beta parameters simultaneously, and then it averages all the component parameters and treats the variance parameters essentially as known, and based on these known parameters then again estimates the beta parameters. So this is why there's this 2-pass procedure, which is also kind of documented in the SPM book, but also not that greatly, or not that. It's not that of people's concerns. If people actually then do contrast, they of course use both information from the beta parameters and the variance parameter estimates, because you get only t values if you do that. I think, however, if people visualize parameters, they always only visualize beta parameters and not the variance parameters, so they often get completely lost and not talked about. So let's have a look what we have after estimation. So what you can see is that there are 3 volumes corresponding to the beta parameters. So each volume has the estimated beta parameters for one condition. One can look at them, of course. Maybe, let's use this. So these are the beta parameters, and you might see, for example, here, that the beta parameters here in the back of the brain on the right side are quite bright, which is of course due to the fact that we here presented left visual hemifield checkerboard. So the beta parameters pick up the fact that the both signal increased whenever there was a stimulus here. And of course this is also what you then see essentially in terms of the contrast. What else do we have? So these are the variance estimates, although one cannot really see much. There's a lot of variance here. I wonder, what is this? What's this? Oh, these are the variance estimates. I think RPV versus they relate to the variance. I'm not quite sure right now which one is the. Wait. One of them. not quite sure about these. So one of them, wait, results per voxel. Maybe this. So these are the results. Wait a second. Maybe it just says it on that. So yeah, so this just said it. So this is the variance estimate, and the other one is the result estimate, because this is one thing that I haven't done in the other course yet. It also estimates the smoothness in terms of the partial derivatives of the errors, which is something that we haven't discussed in the other course, and of course needs results, and first then does this over voxels and then averages them. So these are the results per voxels which it needs for the p-values. So I've clarified that. And there's some mask. What is the mask? That's just essentially the brain mask. So these are these images that are created. So brain mask, variance estimates. No, wait, yeah. This is not that easy. So this is the reason some squares. Where are the variance components? I think they might also be in the SPM MUD file. Not clear. Anyway, everybody's only interested in the beta parameters anyway. But based on these estimates, one can then do contrasts, and one can of course do this via the SPM interface, which is what we're doing now. So now we have estimated it, then we can define, for example, T contrast. So let's define a new contrast. Let's call this S1, S2 larger than baseline, for which we say 1, 1. So this is our contrast weight vector. So 1 for this, 1 for this. We don't need to include a 0 for the session offset. So everybody's happy about this. And then we are where we actually started the other course, where we don't apply any thing, and then decide this sort of a confusing thing on the cluster forming threshold, where we use the 0.001. Then we can define on the extend threshold, as we discussed, that only matters for the set level inference. So let's give it 0. And then we get our SPM table with our p-values that we discussed, corrected p-values. So again, in our other course, we discussed this thing here. We discussed this column, and this column. We did not cover the FDR. And we discussed this column, this column, this column. This is this Z equivalent, which is still there. Oh, we didn't do the FDR. So be reminded, we didn't do the FDR, but we did everything else. And here are also things that relate to our statistics, which I still have to document a little bit more. But as you can see here, of course, we get, for this contrast, we get quite some activation in right visual cortex, because from a single session, because we get stimuli on the left visual hemifield, which creates this con image, which is the this is the weighted beta parameter based on the contrast weight vector. These con images, they are sometimes then used for second level analysis, and it creates this SPMT image, which we just saw, and which is then the basis for the p-value evaluation using random field theory, which we do in the other course. So in terms of coding, this is relatively straightforward. So of course, one can, again, via the GUI, specify a contrast manager. One needs to specify the contrast name, like we just did in the GUI, and a contrast weight vector, like we also did in the GUI. And then one can, of course, put in multiple contrasts if one wants to compute multiple contrasts. And then, similar to the sessions and onsets. For each contrast, there's a contrast name and a contrast weight vector, which is then applied and being evaluated. And then one can also create the SPM. That's interesting. The SPM result that we just did, and here you see that there are thresholds, and I didn't really write a comment yet because I wanted to actually clarify in the other course what these things really are, which I've done now. So at one point I can fill that in here. So if we run this, so let's maybe. Let's just run the whole GLM again, although then it's estimating again, but this doesn't take that long. Then this code now in this GLM function does the whole thing from bringing together the data and the design. So model formulation, model estimation using this restricted maximum likelihood approach, and model evaluation in terms of, in this case, T contrasts, and then p-values based on random field theory. And that's GLM analysis of FMI data. And then it's over. Then it's over. So I'm just estimating it again for the fun of it. And then, of course, what one usually does is that one doesn't analyze only a single session, but multiple sessions, usually then with a block diagonal design matrix, so parameters for each session, which then by means of contrasts are collapsed over sessions. And then in this first level, second level analysis takes the con images for single participant parameters to the second level, as they say. So one basically gets, evaluates a better parameter estimate for each voxel for each participant. And then if one has 12 participants, one has 12 values for each voxel, which correspond to better estimates on the first level, and does a one sample t-test over them. So now this just ran again and shows that indeed it can be automatized, that the whole thing ends on this. And then it's over. Then you do a multiple testing procedure by deciding that you report this because it's significant, as we discussed this morning. It's over. There is not more to do. And so in terms of, so if some master students watching this video or not, what we have done here now is, of course, for one subject, doing the pre-processing for one session, and of course the task, if you want to do your project report and so on, then the task is to generalize this now to multiple sessions and multiple subjects, which can be done using for loops. And so talking to people now watching the video, so it might make sense if you want to discuss more details of your project report to think about what this means that you generalize this, and then discuss questions next time, because the next time is the last session, and then I will expect your project report at the end of September. And for EEG, which we will not cover then this term anymore, it works exactly the same way. So you have to specify data, you have to specify some default parameters, you have the problem that you don't quite know what SPM is doing, and but you can use a toolbox, and everybody thinks this toolbox is great. 70% of people in the brain imaging field use SPM. That's what I will write in my paper, because there is a paper from 2012 which found that in a sample of 200 or so studies, and there's this paper from this year where they did this survey in 150 people, and they say that 70% they use SPM. So my best estimate for what people actually do is that 70% use SPM. Any questions?
Why don't you estimate the beta parameters for all the data using multiple sessions in each participant? I mean, so what? I mean, you just said you estimate one, or like the beta parameters for each run, right? Like if you have 5 runs, you have 5 beta parameters of each kind for each participant. Why can't you just say, okay, I collapse all the data?
Can also do that. I mean, this. The question is how much. This is a good question. So the essential. I mean, you get a little bit more freedom in terms of the beta parameters because you can look at the beta parameters of a specific run. But then the bigger question is whether the average over these beta parameters from over sessions is the same as if you would do it together, which I think under the most benign assumption is the case. But yeah, it is implemented here is that you do it differently over session. So that you may account for session differences. Yeah, but you can also do that for using offsets. So this is more like the default way. I mean, the bigger question is why this whole thing is not hierarchically estimated, in the sense that you use information from the other subject to also inform the estimation of the beta parameters for a single subject. This is essentially how FSL does it, with all the idiosyncrasies that come into FSL. The thing is, of course, that if you are familiar with hierarchical linear modeling from a psychological background or so on, the data sets are of course smaller usually, and you don't have as much data as you have here. So I think this is why traditionally this two-step procedure was chosen, so that you really go step by step over voxels and over participants. It's not, I think there is also a hierarchical approach to this that I think is even implemented in SPM somewhere hidden, but it's not what people usually do. And so I'm just reporting here what people usually use, that they use this two-step procedure. The problem in the whole field is that people think that there is the right way to analyze the data, and that they think that the default way that SPM does it is the right way because SPM was created by the smart people, and so we all do what the smart people think. And this is the reasoning by a lot of people in the brain imaging field, which is horrible, and which just means that a lot of people should just leave the brain imaging field. It's just, this is one way how one can do it, and it's not that the people who developed SPM had the intention to say this is the only way to do it. They just made a proposal, this is how one can do it, look, we have implemented it, now you can use it, it's great, it helps you maybe, but you can do it differently. Nobody said this is the right way, and nobody said that the way that you do this kind of weird, not spatial modeling the whole time, but in the very end, at the level of the p-values, you bring in the random field theory. Nobody said that this is the right way or the best way. They just said this is one way. But people from backgrounds that don't necessarily enable them to develop their own data analysis think that this is the right way because it's in the software, and that people decided that this is the right way. Nobody ever did that. But still, this then is so community that what SPM does is the way to do it, and then you can write this paper like, look, SPM sometimes has a different false discovery rate, and then it's like, oh, we are all doing something wrong, it's all horrible. And it's like, this was never, nobody ever said that this is the right way. People just did it, and most people assumed that this would be the best or whatever. It's all horrible. This whole cognitive neuroimaging, brain imaging field is just, oh no, leave me alone. No, it would be so much. It would be so much more fun, the whole thing, if. Well, I'm waiting for my. Actually, today we're supposed to hear from computation and neuroscience. If people were just independent researchers in this freaking field of cognitive neuroimaging and not toolbox users. I go crazy. I have to stop recording this. Otherwise, I will. But nobody's watching this anyway, so I can say whatever I want. Good. Any other questions?